Okay, so this is our code for lab assignment 2, where we had to create a 4x16 decoder. So first, we had to create our decoder module. And right here, I called it decoder underscore n bits. And the reason why is because I utilized this parameter construct. So basically, wherever n is stated in the code, it'll replace it by 4. And so that allows us to sort of customize whatever size decoder we want. So if I change it to 5 or 6, it'll just give us a 6 input, and then the output would be 2 to the n power. So for our inputs, it'll be 4 minus 1, which is 3 to 0, and that'll give us our 4 inputs. And we have our enable input as well. And for our output, it is 0 to 2 to the n minus 1, which is 15. So 0 to 15 will give us our 16 outputs. Next, we decided to model our function of the decoder in an always block. And so we put the always right here with our sensitivity list where X and enable is bound to change. So that way the code will execute when it changes. And so we set Y as 0 as sort of a default to clear it. And we have an if else statement. If enable is on, it'll execute this line right here. And this line basically says that say X is equal to 0, then Y of 0 will turn on. It'll set to 1. So whatever that position is, the output is, it'll turn on. And that's what we want with a decoder. And if the enable is turned off, it'll just turn everything off, so it won't display anything. Okay, moving on to our test bench. So for our test bench, again, we have to state our parameter. And for our inputs, we put reg for all of them. And our output is wire. And then I stated an integer here because we'll be using it in a for loop later on. And after that, we have to instantiate our module. So that's why I call it here. And again, here's our parameter. And then I just called it test bench. And then basically we wire the variables used in this module to these right here. And that's why we have this form. And so we have to put in values. So we start with an initial and then begin and end. And first I turn on the enable bit and I let it wait for 10 nanoseconds. And then I use this for loop to cycle through our truth table. So that those are numbers 0 through 15. And that'll basically set our X to whatever K is on. And it'll wait 10 nanoseconds in between so we can see it in the simulation. And after that's all executed, it'll wait a bit more, and then that's the end of our simulation. So with our simulation, let me zoom out. So starting from 0, enable is on, and we can see the first position is turned on. And as we cycle through, here's 1, it'll shift over to the next position. And as I move along, it'll keep shifting to the right. So that's 5, 6, 7, 8, 9. That's supposed to be 10, 11, 12, 13, 14, and 15. As for our constraints, our I/O ports, I used switches 0 through 3 for our inputs. I used the very last switch for our enable switch. And then we used all of the LEDs to show all 16 of our outputs. This is our lab assignment 2 demo for our 4x16 decoder. So first I mapped our 4 inputs as switches 0 through 3, and I put our enable bit switch to switch 15. That'll turn on and off the decoder. So right now it's switched on off. And so if we try to switch the inputs, the LEDs don't turn on at all. But once I turn on the enable bit, it'll turn on. So the way I designed our decoder, I used this truth table right here. So basically at 0, 0, 0, it will turn on this position right here, and I mapped M0 to LED 15. And so if I switch on number 1, it moves to the next position. And as we can see, 0001 is at M1. And so it should continue down the line, just like the truth table. So here's 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, and 15.